Welcome to the deep dive. If you've ever found yourself just staring at a blinking console light or, trying to figure out why the network suddenly feels like it's wading through molasses, well, it takes a whole bunch of tools to keep things flowing.
That's absolutely right. And today, we're not just like listing tools. We want to really get into the thinking behind them, the hierarchy.
Yeah, exactly. Our mission today is to give you a sort of fast track, right, through how network operations has evolved.
We're looking at the command line basics, the foundational stuff everyone starts with. Then we'll get into the bigger systems, these network management platforms, NMPs.
And finally, the modern stuff, the automation tools like Ansible, which are, frankly, changing the game for NetOps teams, turning it from just fixing breaks to something, well, more proactive.
We've pulled together material covering 5 main categories of tools based on RFCs and just common practice. Then NMP architectures, how data gets visualized.
Right, and automation principles and even the licensing models. It's quite a journey from diagnosing one bad link to basically orchestrating whole data centers.
So let's kick things off where everyone starts, the command line, the foundational toolkit.
Our sources lay out these 5 key categories: status monitoring, traffic monitoring, network routing tools, SNMP stuff, and traffic generation.
Okay, status monitoring, ground zero. The classic tool, everyone knows it, is ping.
Right. Checks if a device is alive, if it's powered on. Simple.
But it's more than that, isn't it? Ping gives you that round trip time, the delay, and the TTL, the time to live. That tells you how many routers it hopped through. It's basic, but yeah, still the first thing you run.
Absolutely. Then you got to check your own house, right? Your local network interface. Historically, that was ifconfig or ipconfig on Windows.
Shows you if the interface is up, your MFC address, your IP address, the basics.
But it's interesting how fast this stuff changes. The sources we looked at really hammer home that ifconfig is, well, outdated now.
It really is.
Yeah.
Because modern networks, they just need more detail. The official replacement in Linux is the IP command. It's much richer.
So instead of one command, you use specific arguments like iplink or ipaddress.
Exactly. Much more flexible, gives you way more detailed info on interface states, stats. Crucial for scripting today.
Okay, so your machine's healthy. Now you need to talk to the world. DNS troubleshooting, super important.
Yeah, the classic tools here are islookup, dig, and host. They all basically do the same job, right?
Testing if your DNS servers can actually resolve names to IP addresses.
Exactly. If you can ping by IP but not by name, these are your go-to tools. First stop.
Okay, so moving beyond just basic is it up, let's talk routing, testing the actual path.
Right. And another classic tool that's largely replaced now is ARP. Remember ARP for the Address Resolution Protocol cache.
Oh, yeah.
Today, that's handled much better by the ipneighbors command in modern Linux. Again, it's that trend. More specific, richer tools replacing the old general ones.
And the most dramatic change here, I think, is traceroute. We all use traceroute, watching it hop along.
Slowly. Painfully slowly sometimes.
Yeah. And it only gives you a snapshot, right? Not great for diagnosing problems happening now.
Which is why the sources really point to its replacement. MTR.
Yes.
It's such a game changer. Because it's live, it's interactive, it keeps sending packets, and shows you the delay and loss for every single link on the path. Continuously.
So if there's a bottleneck, like 7 hops away dropping packets.
MTR nails it.
Yeah.
Instantly. You see it right there. That shift from just snapshot testing to continuous real-time monitoring. That's kind of the whole story of modern NetOps in miniature.
Okay, good point. And how do you check the actual routing table itself?
On Linux, it's iproute, or just route still works on Windows. Shows you where your system thinks packets should go.
Got it. So we have status and routing checks covered. What about monitoring the actual flow? Traffic monitoring.
Well, we listed ping again here, and it's worth mentioning why. That round trip time is key for understanding the quality of the link itself, the propagation characteristics.
Not just is it up, but how good is it?
Precisely. But if you really want to see what's inside the packets, you need traffic sniffing.
Right, turning your machine into an observer, basically grabbing packets off the wire.
The 2 big ones here are TCP dump, the command line workhorse, and of course, Wireshark.
The GUI powerhouse. Everyone loves Wireshark.
Or its command line version, Tshark, if you're on a server without a GUI. Very handy.
And the key here is filtering, right? You don't just drink from the fire hose.
Exactly. You filter by protocol, maybe port, IP address, so you only see the traffic you actually care about. Makes analysis possible.
Okay, now let's switch gears a bit. SNMP, the Simple Network Management Protocol. If you're managing network gear, You need SNMP tools.
Absolutely fundamental. And the core utility here is SempWalk.
Right, so explain SimpWalk. If the device's data is like a big filing cabinet, the MIB.
The management information base, yeah.
Mhm.
Think of it as a structured tree of information, CPU load, interface counters, temperature, everything. SempWalk basically says, walk down this branch of the tree and give me everything you find.
It sends those get next to requests over and over.
Until it gets the whole subtree you asked for. It's how you remotely pull status and config data from devices. Essential.
And what about testing your management system itself? Say you set up a new NMS, you want to see if it catches alerts.
That's where SempTrap comes in.
Right.
SempTrap lets you generate fake traps. Those are the asynchronous alerts devices send when something bad happens, like an interface going down,
So you can use StemTrap to send a test alert to your NMS.
without actually breaking anything on the network. Lets you verify your alerting rules and processing are working before a real problem hits. Really useful for validation.
Makes sense. Okay, final category of these foundational tools. Traffic generation. Sometimes you need to, well, stress things out.
Yeah, diagnostics are one thing, but sometimes you need to test capacity or performance under load. You need tools to generate controlled traffic.
Specific types like TCP or UDP, right?
Exactly. The standard open source tool here is iPerf, or the newer iPerf 3.
How does that work?
Simple client-server model. You run iPerf in server mode on one machine, client mode on another. It blasts traffic between them, and you measure the throughput. You can specify protocols, ports, things like that.
Okay, so iPerf tests performance with standard traffic, but the sources mention another one, Packeth. How's that different?
Packeth is more specialized. iPerf tests how your network handles normal traffic. Packeth is for when you need to craft custom packets.
Like for testing a new protocol implementation or security vulnerabilities?
Precisely. It gives you a UI to build packets byte by byte if you need to. Total flexibility, but for very specific use cases, usually development or deep security analysis.
Okay, wow, that's quite the toolkit just at the command line. But like you said, you can't manage 1,000 devices just using SSH and ping, right?
Not realistically, no. That's where you absolutely need an integrated system. The network management platform, the NMP.
This is the brain, right? The thing that brings together all those management functions. FCAPS.
Yeah, the classic acronym, fault, configuration, accounting, performance, and security. A good NMP tries to cover all of these.
So architecturally, what are the key pieces of an NMP?
Well, they need to be modular. They rely heavily on protocols like SNMP and ICMP for discovering devices on the network. LLDP is also used a lot now for discovery.
And they need to understand different vendors.
Crucially, yes. They need the ability to import vendor-specific MIBs so they know what data to pull from a Cisco switch versus, say, a Juniper router. And security access control, that's vital too.
But you mentioned a limitation with SNMP earlier.
Yeah.
It doesn't store history.
Exactly. SNMP gives you the current state. That's the CPU load right now. It doesn't inherently store what it was yesterday or last week. For that, NMPs need databases.
Right. And this is where it gets really interesting, according to the sources. Not just any database, but time series databases, TSDBs. Why are they so important for network performance data?
Because network data like interface counters, CPU load, over time, it's fundamentally time-stamped data. It comes in constantly sequentially. And when you query it, you almost always care about the time range.
So regular SQL databases aren't good at that.
They can do it, but TSDBs are optimized for it. They handle massive amounts of incoming data, high write throughput. They index based on time, so querying date range is super fast.
Okay.
Plus, they often have built-in features for automatically downsampling data, like storing per second data for a day, then per minute data for a week, then hourly forever. And compression saves a ton of space. And they manage data retention, automatically deleting old data.
So trying to stuff millions of counter updates per minute into a standard SQL database would just choke it? And asking, what was the average link utilization last Tuesday would take forever.
Pretty much, yeah. TSDBs are built for exactly that workload. Let's look at a few key ones. RRD tool, Round Robin Database tool, one of the originals.
What's its main idea?
Its big innovation was using a circular buffer. Imagine a fixed size file. When new data comes in, the oldest data point just gets overwritten.
So the storage size never grows.
Exactly. Stays constant forever. Revolutionary for its time when storage was expensive. Kept things predictable.
Okay. And the modern big players, you mentioned InfluxDB.
Yeah, InfluxDB, often used with the TechID stack. Telegraph collects, Chronograph visualizes. It has its own SQL-like query language, InfluxQL, or a more complex scripting language called Flux.
And how does data get into InfluxDB?
Typically, it's a push model. The monitoring agents or the devices themselves actively send their metrics to the InfluxDB server.
Okay, push model. And its main competitor, you said, is Prometheus?
Prometheus is huge today. It uses a query language called PromQL. The key difference is it generally uses a pull model.
So Prometheus reaches out.
Exactly. The Prometheus server actively scrapes metrics from configured targets, devices, or applications at regular intervals. Those targets just need to expose their metrics on a simple web endpoint.
Why is pull often preferred now?
It can simplify configuration. The central server controls the polling. The targets are often simpler, just needing to expose data. Easier to manage discovery sometimes.
Interesting. Okay, let's talk about how these databases and concepts actually show up in real-world systems. Open source NMPs. The source is mentioned Nagios.
Nagios is a classic. A very complete, very powerful system, great for infrastructure monitoring, complex alerting, reporting, even planning maintenance windows.
But maybe a bit complex to set up initially.
Historically, yeah, it had a reputation for a steep learning curve. Very flexible, but takes effort.
Okay. And if Nagios is the veteran, maybe Zabbix is the modern challenger.
Zabbix is incredibly popular now, really strong on distributed monitoring. It can collect metrics from almost anything. It has smart thresholding, even trend prediction to help with capacity planning. It's quite comprehensive.
Then there was a more focused example, Observium. What's its niche?
Observium is primarily focused on performance management, graphing data gathered via SNMP. It's really good at that.
But maybe not the full FCAPS picture.
Right. The sources noted it has pretty limited topology discovery and mapping compared to Nagios or Zabbix. So you get great performance graphs, but maybe not that visual network map.
And of course, on the commercial side, there are giants like SolarWinds, vendor agnostic, widely used in enterprises.
Definitely a major player in the commercial space.
So you collect all this data, whether with Nagios, Zabbix, or something else, but just having numbers isn't enough, right? Visualization is key.
Absolutely critical, turning potentially millions of data points into something a human can understand quickly. That's the goal.
Like Cacti? What was that again?
Cacti is basically a web front end specifically designed to graph data stored in RRD Tool. It made those RRD Tool databases accessible, tuning the raw numbers into historical trend graphs you could view in a browser.
Okay. And then Network Weather Map. I always like the idea of that one.
Yeah, it's very intuitive. It literally draws your network links on a map, maybe a geographical map, maybe a logical one, and colors the links based on utilization.
So like green is good, yellow's getting busy, red is congested.
Exactly. Instant visual cue for hotspots. But importantly, Weather Map doesn't collect the data itself. It needs another tool like Cacti or maybe MRTG to feed it the utilization numbers.
Got it. It visualizes data from elsewhere. And the modern king of visualization seems to be Grafana.
Grafana is everywhere now. It's open source, incredibly flexible. It can connect to tons of different data sources, Prometheus, InfluxDB, SQL databases, cloud sources, you name it.
And lets you build custom dashboards.
Totally custom dashboards.
Right.
Graphs, gauges, heat maps, tables, world maps. And it integrates alerting, too. Its power and flexibility connecting to anything is why it's become the de facto standard for visualization in many tech stacks.
Okay, so this whole journey from a single command line tool like Ping all the way up to these big NMPs with Grafana dashboards, it shows the need for scale. But even NMPs need configuration, right? Maintenance.
Constantly. And that's where the next evolution comes in. Automation.
Tools like Puppet, Chef, Terraform, and the one we focused on, Ansible. Why is automation so essential for NetOps now?
Speed and consistency. You need to configure hundreds or thousands of devices, scale services up and down, integrate things quickly. Doing that manually is slow, error-prone. Automation makes it faster, repeatable, and much less likely to have errors.
Let's focus on Ansible. The sources highlighted its key advantage, especially for networking. It's agentless. Why is not needing an agent on the network device such a big deal?
Because network devices, routers, switches, firewalls, they're often closed boxes, especially older gear. Installing custom software agents on them can be difficult, sometimes impossible, or void warranties.
So how does Ansible talk to them?
It uses standard protocols you already have, primarily SSH, Secure Shell. No extra software needed on the managed device itself. That simplifies deployment and management massively.
Okay, but here's the bit I always found tricky. Ansible is written in Python. Servers usually run Python. But a Cisco router doesn't. So how does Ansible configure a router?
That's a great question, and it's key to understanding Ansible for networks. It happens on the control node.
The machine where you actually run Ansible from.
Exactly. When Ansible talks to a Linux server, it can basically push small Python scripts over SSH for the server to run locally.
Yeah.
But for a network device,
Yeah.
the Ansible control node runs the necessary Python logic itself, figures out the right sequence of CLI commands needed for that device type, Cisco iOS, Juniper Junos, whatever, and then sends those text commands over the SSH connection to the router's console.
So the Python runs on the control node, and it just sends the familiar CLI commands the router understands.
Precisely. That's the magic. It translates the abstract task into device-specific commands.
That makes so much sense. Okay, so let's quickly run through the Ansible basics. You have the control node. You need a list of devices.
That's the inventory file. Can be super simple, just a list of IPs or host names. But you can also group them logically, like spine routers, leaf routers, web servers, lets you target specific groups.
And for quick one-off tasks.
You use ad hoc commands, like Ansible all mping just checks connectivity to everything in your inventory. Simple, quick checks.
But the real power is in playbooks.
Absolutely. Playbooks are where you define complex, multi-step configurations. They're written in YAML.
Which is meant to be human-readable, right?
Yeah, reasonably easy to read and write, lots of indentation. Playbooks have structure. You specify which hosts the tasks apply to, the connection method, like networkly for routers. You can define vars, variables, and then you list the tasks.
And each task uses an Ansible module.
Right. There are thousands of modules. For network gear, you might use iosconfig for Cisco, junosconfig for Juniper, etc. These modules contain the Python logic to generate the right CLI commands.
And there's another key principle, idempotency. Sounds complicated.
It just means the task only makes a change if it needs to. If you have a task to ensure VLAN 10 exists, and VLAN 10 already exists on the router, Ansible checks, sees it's there, and does nothing.
So you can run the same playbook over and over.
And it will only apply changes necessary to reach the desired state described in the playbook. It doesn't just blindly run commands. Super important for safety and consistency.
Okay. Wow. That covers a lot of ground, from basic tools to full automation. But we have to touch on the practical side, cost, licensing these systems. It's not straightforward, is it?
Oh, definitely not. Licensing models for NMPs and related tools vary wildly. It's often a major factor in choosing a solution.
What are the common models?
One simple one is per node. You pay based on the number of devices, switches, routers, servers you're monitoring. Sometimes there's a freemium model, free up to, say, 10 devices, then you pay.
Okay, seems reasonable. What else?
It can get more granular. Some vendors charge per interface. So the big 48-port switch costs more to monitor than an 8-port switch, even though it's just one node. That can add up fast.
Right. And even more granular.
Yes, the per sensor model.
Yeah.
This is really detailed. Monitoring, say, bandwidth utilization on an interface might be one sensor. Monitoring CPU load on the same device is a second sensor. Temperature, a third. You pay for each individual metric you track per device.
Wow, that forces you to be really selective about what you monitor.
It does. You have to prioritize what data is actually worth paying for. And finally, for things like log management systems, the model often shifts entirely.
How so?
It's all volume-based. You pay based on the amount of log data ingested or stored, maybe gigabytes per day, not necessarily the number of devices sending logs.
Okay, lots of different ways to slice it.
Definitely. We've covered a huge amount today, from just a simple ping or MTR through these big NMP systems built on specialized databases like TSDBs, all the way to automating entire network configurations with Ansible.
It really feels like effective network management isn't about finding one magic tool.
Not at all. It's about understanding all these pieces, the command line tools, the monitoring platforms, the databases, the visualization, the automation, and picking and integrating the right mix for your specific network. Its size, its importance, it's modular.
So here's a final thought for you, our listener, to think about. It's a trade-off every NetOps team faces. You have these powerful, highly customizable open source platforms like Nagios or Zabbix, but they often demand significant upfront time and expertise to set up and maintain correctly.
Yeah.
On the other hand, you have polished commercial solutions like SolarWinds, which might be easier to get running but come with substantial licensing costs, that budget impact. So the question is, where would you prioritize your organization's investment? Would you invest more time mastering the complexities of open source or more budget on the potential ease of use of a commercial system, all to achieve the best possible network reliability and scalability in the long run? Something to consider.